Hello and welcome to this tutorial on decision trees. In the preceding lectures, we have looked at some of the theory behind decision trees. In this tutorial, we will get some hands-on experience actually building trees using some of the concepts we have learned. For building decision tree models with real data, we will of course resort to packages such as Weka. However, in this tutorial, we will be building trees for a very small data set in order to understand the process involved in building decision trees. This is the data set we will use for this exercise. As you can see, there are 4 different attributes with a binary valued target, that is Bayes computer. Note that the attributes age and income can take 3 different values, whereas student and credit rating are binary valued. In the theory lectures, we have already seen the different options available to us when building binary trees. For example, the first thing we have to consider is the type of tree which we want to build. We can either have binary trees or multiway trees depending upon the branching factor at each node. Another option available to us is the impurity measure used. In this tutorial, we will be looking at 2 different impurity measures, which are cross-entropy and the Gini index. Another option which we don't consider here is the pruning technique used. To start with, let us try and build a tree using multiway splits and cross-entropy as the impurity measure. The first thing that we have to do is to identify the root node. This is done by considering each attribute in turn, calculating the cross-entropy value for that attribute, and identifying the attribute which gives us the lowest value. Let us start by considering the attribute age. From the table, we observe that the attribute age can take on 3 distinct values, which are youth, middle-aged and senior. Going back to the formula for cross-entropy, we see that for each node we need the proportion of class K observations in that node. In case of a 2-class problem such as the one we are considering, we can use the simpler expression minus p log p minus 1 minus p log 1 minus p, where p is the proportion of observations for the positive class. Since we need to calculate the cross-entropy for an attribute with 3 distinct values, we will have 3 components. Let us first consider the value youth. This is highlighted in the table. We observe that out of the 14 different data points, 5 observations have age equals to youth. Among them, 2 are belonging to the positive class and 3 belong to the negative class. Using this information, we have minus 2 by 5 log 2 by 5, that is the proportion of observations belonging to the positive class, and minus 3 by 5 log 3 by 5 for the negative class. This expression is multiplied by the ratio 5:14, which indicates which is a normalizing factor, since 5 out of the 14 data points had age equals to youth. Continuing with this manner, we take up the next value, that is age equals to middle-aged, and observe that among the 14 there are 4 points where age equals to middle-aged, and for all of them Bayes computer equals to yes, that is they all belong to the positive class. This gives us the second component. As you can see, we don't necessarily need to calculate this, but we have put it there just for your reference. The final component comes when we consider age equals to senior. Again, there are 5 points with age equals to senior. Of them, we observe that 3 belong to the positive class and 2 belong to the negative class. Putting it all together, we get a value of cross entropy. Note that all logarithms used here are using the base 2. Make sure that you are able to follow the calculations, especially how we were able to write down each of the components of the cross entropy expression. Using the same process, we now consider the attribute income and find the cross entropy bill. Next, we find the cross entropy for the attribute student and the cross entropy for the credit rating. Note that here we have only two components because both of these are binary valued. Finally, we compare each of the cross entropy values, and in this case observe that the attribute age gives the lowest cross entropy value and hence is the optimal attribute to use as the root of our decision tree. Thus we obtain the partial decision tree with age as the root attribute and 3 branches corresponding to the 3 distinct values that the attribute age can take. Note that the middle-aged, that is the branch where age equals to middle-aged, has been labeled with yes, indicating that this is a leaf node where any observation following along this branch will be labeled yes. This is because if we go back to the table, we observe that when age equals to middle-aged, Bayes computer equals to yes. Thus, along this branch of the tree, there is no need to further grow the tree, since from the training data given to us, we can directly conclude that if we observe age to be middle-aged, then we can label the the observation as positive, that is the person will buy a computer. Now we have created this partial decision tree, so how do we proceed? Essentially it is a recursive process. We started at the root node, we were able to find the root node to be the attribute age. Now along each of the remaining branches where we have not found the node to be a leaf node, we have to repeat the same process. So let us first look at the branch age equals to youth. We have already considered the attribute age, so there are 3 attributes left to us. Using a process similar to what we have just seen, we try to identify the best attribute to use at this position. So we consider the cross entropy of income where age equals to youth. Now we will not be considering the entire data set, but we'll consider the restricted data set where age equals to youth. This is illustrated in this table where we have crossed out all observations where age is not youth. So essentially we repeat the same entire process with this restricted data set. Note that the attribute age has already been considered, so we are left with the remaining 3 attributes, and these are the values that are to be considered. Thus we have cross entropy of income when age equals to youth. You can go back and verify that these are the values you will obtain. Next we have cross entropy of student when the age is equal to youth. Here we observe that the cross entropy is actually 0. Going back to the table, we see that when age equals to youth and student is no, Bayes computer is no, and when student is yes, Bayes computer is yes. So this leads us to a pure leaf. We can go ahead and calculate the cross entropy for credit rating as well when age equals to youth, but since we will not get a value less than 0, we can stop the process here and get the partial tree where we have selected the attribute student with the least value of cross entropy. As you can see, we have labeled the branches yes and no, because these are leaf nodes which are pure, there is no mixture. Now as you can see, we have this branch, and this branch are all leaf nodes. So the remaining branch to consider is when age equals to senior. Again, we look at the table where we disregard all observations where age is not senior and follow the same calculations. We get cross entropy when we look at income when age is equals to senior, and cross entropy of student when age equals to senior, and cross entropy of credit rating when age equal to senior. Here again we find a cross entropy value of 0, which is the minimum, and if we go back to the table, wherever credit rating is fair, we have bias computer equals to yes here as well, and whenever credit rating is excellent, we have bias computer is equal to no. So this allows us to create a decision tree where each of the leaf node is a pure node. In case we did not get a cross entropy value of 0, let's say we had a different value of cross entropy here, we would again continue the process, and the last situation is when we have exhausted all attributes available to us and we still do not have a pure leaf. What do we do then? Essentially, let's say when we follow this branch, there were 5 points, of which 3 were positive and 2 were negative. Then this would have been labeled yes, because the majority of the data points have a positive belong to the positive class. Fortunately for us, in this example we have obtained all leaf nodes as pure, but this will not always be the case. Next we will look at decision trees using Multiway Split and the Gini index. Essentially the process is the same, except that we replace the cross entropy measure with the Gini index impurity measure. This will be left as an exercise. Now the other type of tree that can be built is a binary tree. For this exercise we will look at using the Gini index impurity measure. Recall that when we were creating multi-way trees, to select an attribute for a node, we had to consider each attribute only once. However, in the case of binary trees, since for each attribute there may be different subsets to consider, that is where to split, we may have to look at attributes multiple times. Also, as was mentioned in the theory lectures, in case of a binary outcome, we can reduce the number of partitions that have to be considered by ordering the values according to the proportion belonging to the positive class. Since our data set has binary valued outcome, we will see how this process works. Again, we start by considering the attribute age. As we can see from the table, age can take 3 distinct values. Now we look at the positive class proportions for each of the values. We see that when age equals to youth, 2 out of 5 observations belong to the positive class. For age equal to middle-aged, each of the 4 observations belong to the positive class, and when age equals to senior, 3 out of 5 observations belong to the positive class. Thus we have an ordering for the attribute age, youth, senior, and middle-aged. What this essentially means is that we have 2 possible split points, youth along one branch and senior and middle-aged along the other, or youth and senior along one branch and middle-aged along the other. Note that the attribute age actually has a notion of order, that is youth, middle-aged, and senior. If we want to retain that notion of order, then we would only consider the split points where youth is along one branch and the other 2 are along the other branch, or youth and middle-aged is along the one branch and the senior is along the other. We have considered the attribute age unordered here to illustrate how you would go about ordering values. For the rest of this exercise, we will use this specific ordering for the attribute age. Now that we have identified the possible split points, we estimate the impurity measure here using Gini index for both possibilities. Note that since we are in a two-class scenario, we use the simplified formula of the Gini index equals to 2p into 1 minus p, where p is the proportion of observations belonging to the positive class. Go back to the table and verify that these are the values obtained. We see that when we calculate Gini index, where we are considering the split where youth is in one branch and the remaining two are in the other branch, we get a value of 0.6508, and where we consider the alternate split where youth and senior belong in one branch and middle-aged belongs to the other, we get a lower value of 0.3571. Thus, among these two, this is the split that would be preferred. Now, this calculation is just for the attribute age. We need to repeat the same process for the remaining three attributes. Thus, we have the attribute income. Going back to the table, we will see that this is the ordering for the three values that the attribute income can take and the corresponding Gini index values. And next we have the calculations for the attribute student and credit rating. Here there is only a single possible ordering because both of these are binary valued attributes. Finally, we compare all the results and we observe that the attribute age, where the split is with youth and senior along one side and middle-aged along the other, is the optimal, gives the optimal value, and thus we select this particular attribute with this particular split point as the root. Thus we create this partial decision tree. Again, from our previous exercise, we know that when age equals to middle age, all our observations are positive, so we do not need to grow the tree beyond this. Thus, now we focus on the branch where age equals to youth or senior. So again, from previous experience, we know that to create to grow the tree along this branch, we need to consider only observations where age is youth or senior. Thus we have disregarded all observations where age equals to middle-aged. Now we repeat the same process. We have already consumed the attribute age. We have three remaining attributes. Of these, income has three distinct values, so we need to identify the optimal split point. That is, we need to first consider the ordering shown here. For student and credit rating, both are binary valued, so there is only going to be one split point. So if we repeat the calculations for this subset of the data set, we will identify that the next node should use the attribute student. However, this is not the end, since we do not obtain pure nodes here, and this process has to be continued. Again, we will leave this as an exercise. Hopefully this tutorial would have clarified some of the concepts that we came across in the theory lectures and helped you in understanding how decision trees are created. Of course, for real world data as well as the programming assignments that will be released, we will be using a tool such as Weka, where you have a lot more options. For example, pruning, which we were unable to cover in this short tutorial. For any doubts regarding any of the concepts covered here, please use the forums.